We will now discuss various practical issues in terms of sampling for your path tracer. The first thing we need to do is generate a sample in the upper hemisphere. Now this can be done by uniformly sampling the upper hemisphere. One approach to do that is rejection sampling. Generate 3 random numbers x, y, and z, each in the range from -1 to +1. If x squared plus y squared plus z squared is greater than 1, that means it doesn't lie within the sphere, reject. Normalize the x, y, and z values so that they are a unit vector on the unit sphere for directions. And finally, pointing into the surface, the ray dot product with the normal is less than 0, flip and get the negative of the ray. A second approach to do this we've already discussed is the inversion technique. In the polar coordinates, the density is proportional to sine theta d theta d phi. That's the differential of the solid angle. Therefore, you can do CDF inversion. You can integrate this, you can invert, and so you will take cosine inverse. So you start with two numbers, psi1 and psi2, in 0 to 1. Those are generated from your uniform random number generator. You determine phi as 2 pi psi2. Therefore, phi will be uniformly distributed in 0 and 2 pi. Then you need to generate z in 0, 1. Z corresponds to cosine theta. Z is simply equal to psi1. And finally, you net theta is equal to the inverse cosine of z, which is simply the arc cosine of psi1. Thereafter, you convert into Cartesian coordinates. You're not entirely done at this point because you have obtained the coordinates for the direction you want with respect to the local surface normal. So you now need to do a final step, which is you need to rotate according to the surface normal in such a way that your z direction corresponds to the normal. The normal, let's say, is given by alpha comma beta, where you have a normal nx, ny, and nz, and you can see from the spherical coordinates that that would correspond to sine alpha, cos beta, sine alpha, sine beta, and cos alpha. Therefore, alpha will be given by the inverse cosine of nz, and beta will be given corresponding to nx and ny, which you can obtain using the atan2 function. Then you need a rotation matrix corresponding to alpha and beta, and you need to rotate x, y, and z. In fact, the rotation matrix can be calculated quite simply, and I have listed it on this slide. You can also look at the figure for a diagram of what you're doing. So actually what you're doing is first you're rotating by ry corresponding to alpha, and then rotating around the sphere by rz corresponding to beta. Still a third approach, which is what is discussed in the assignment, is to create a coordinate frame. Recall that a coordinate frame is simply 3 vectors u, v, and w that are orthonormal with respect to each other. That means the norm of each of the 3 vectors is 1, but the dot product of any of them is equal to 0. And furthermore, that w is equal to u cross v. Note that any point P can be expressed in terms of u, v, and w by its projection or dot product onto those unit vectors. We need to create this coordinate frame u, v, and w. The important thing is that the w vector correspond to the surface normal or the surface orientation. Usually the normal will already be normalized, but I have still written it with the normalization. Thereafter, I've just used my standard approach to create a coordinate frame given some auxiliary vector A. It doesn't really matter what this auxiliary vector A is. You can use a random vector or you can use the up vector. However, you have to pay careful attention when A is very close to n, and you have to change the vector correspondingly. Now, once you have done that, you have this coordinate frame u, v, and w. You also have the scalar coordinates x, y, and z that were obtained from theta and phi. And then you can just create the vector for the incoming direction as x times u plus y times the vector v plus z times the vector w. Whichever of these three methods you use, it can be used for uniformly sampling the upper hemisphere and creating a direction on it. At this point, you should be able to do assignment 3, checkpoint 1. You want to sample the hemisphere at each bounce. Effectively, you are considering n is equal to 1 and evaluating the full Monte Carlo estimator with n is equal to 1 for each ray. You go up to depth d is equal to 5. The final ray, when the depth d is equal to 5, does not propagate the ray further, it returns only the emission value. Notice that most rays will actually have a contribution of 0. When I say rays, I use it interchangeably with paths because really you're sampling paths up to depth 5. Note that in most cases you will get up to depth 5 and you will never hit the light source because the light source is only a small part of the scene, and therefore your contribution will be 0. This is an extremely inefficient approach, but it provides a baseline which you will improve on next. Here are some images at 1 sample per pixel. I'm trying to render the Cornell box scene, and I just get a bunch of dots. The reason you're getting dots in some regions is that those dots correspond to where you actually ended up hitting the light source. At the other pixels, you never hit the light source, and so those regions are black. With 64 samples per pixel, which is effectively rendering 64 separate 1 sample per pixel images and averaging them, or correspondingly considering 64 separate n is equal to 1 paths and averaging them, you can begin to see the Cornell box, but it is still horribly noisy.